started, a couple of quick announcements. So, first off, welcome back. I hope your break was relaxing and, wasn't filled with all of these engineering projects that we give you over break, because to us engineering professors, break means, oh, you've got time to do homework. And you're looking at me like,
I think that's
not,
means.
What's that?
I think that's what dead week means to you.
Yeah. Hey, I don't have any projects due on dead week.
Everybody under the great golden sun.
But I can't say that next semester, because it gets real next semester. So. Well, I'm gonna talk about that. All right. So I will still try. I didn't get a chance to post a transportation review, but I'm going to try and post something. Everybody settle down, settle down. I'm going to try and post something sometime, maybe this week or this weekend. If not, I might do it this week and maybe just skip on environmental, because I couldn't do an environmental review myself anyways. I think that's sort of my limit in terms of my area of competency. There's like a biochemical oxygen demand, and that's it. That's all you need to know, right? No, I'm really joking. I'm joking, but yeah. This review is sort of pushing it for me. In fact, I'm not really doing a water resources review today. I'm calling it water resources light, because if I were to try and say that this covers fluids, hydraulics, and hydrology, like that would be a lie. I hope I don't embarrass Dr. Wade too much with my absolute lack of expertise in this area, but I'll do my best. I do want to talk a little bit about the topic poll that you all did. A few comments on the results and some updates and whatnot about next semester. Okay, first off, you all really don't want to do a soils project, like.
Do we really have to tell you why?
Like, woo! That was pretty clear. Transportation was sort of had some interest. Really, other than structures, I would say that the real areas of interest were in environmental and water resources. And there was some significant interest in those areas. So just a little bit of an update on that. I've been in discussions with Dr. Yoon on this about if he's going to be able to take on a team next semester, and it's possible that he is, but I don't have definitive news on that. So because I don't have definitive news on that, I'm not forming teams yet. He's still working out some details. There may be room for a transportation team, maybe, but other than that, it looks like we're going to be doing some structures next semester, because that's pretty much what the majority of people said they wanted to do. I will try and not make you regret it next semester. That was a joke. Not a very funny one. But basically, I have a pretty, I'll go ahead and tell you. I have a pretty well-defined topic where we will start to finish design a highway bridge. And we will design according to AASHTO LRFD. So I will teach you all some bridge design stuff that you haven't seen yet, because we didn't do this in concrete design, and we won't do it in steel design. So while those two classes serve as very nice theoretical backgrounds, it will be new. It will be new material, which is honestly more of a real experience than just regurgitating what you did in steel design or concrete design. When you all get out of here, you're going to go into a design firm or wherever you end up, and they're going to give you something that we never taught you how to do, because we taught you how to be engineers. Okay? So an engineer is going to be presented a problem that they've never seen before. Okay? So that's sort of what I'm going to do. Now at the same time, I'm also going to try and train you a little bit so that when you leave here, you'll leave with a marketable skill. You will be proficient in AASHTO LRFD bridge design, which many undergrads I've never seen before. And on day one, when I show you the bridge spec and show you it's about this thick, and that's just notebook 1 of 2, because there's 2 notebooks that are this thick, you're going to look at me like, oh no. But by the end of the semester, you'll get it. So that's sort of my plan. In terms of forming teams, I'm going to wait because I don't know what's going to happen with the environmental or water resources projects. So that's where I'm at. Does anybody have any questions about senior design?
I have a quick question.
Yeah.
So, do you pick the teams for us, or do we get to pick?
Oh yeah, I'm picking the teams.
Oh, great, thanks.
Oh yeah.
Why?
I don't even like half these
It's
people.
gonna be like,
I don't even like any of them.
I get to pick last, and then it's just gonna be like, alright, who wants Sarah? I want Sarah. Andrew wants me. Can I go on Andrew's too? Way over there.
When are you gonna pick the teams?
What's that?
When are you picking?
He just explained that.
Actually, what she said.
He said it's free to-
But yeah, I'm picking the teams, and I'm doing that for a few specific reasons. But the big one is, you all are going to leave here, and you're going to go work at some Michael Baker or wherever, and you're going to sit down, and somebody's going to say, "Hi, I'm Jackie," and you're going to be working with them. So that's well, then you're going to not have fun at Michael Baker.
Half of us work at the same place anyway, so might as well get to know each other more. She has a point. I'll work with her.
Oh, I'm definitely splitting y'all up now.
I thought it was random generator.
You know, I decided
You
I didn't want to
handpick
go to
it?
Sarah.
There's a little bit of randomness in there, but let me be clear about that. Do I use a random? Hold on. She makes a good point. I'll be absolutely frank. Do I use a little bit of a random number generator? Yes, but I do force it a little bit, and let me explain. What if I had a structures group and nobody in the group had steel design or concrete design at all?
Half of us had steel.
I'm using an example. What if I had an environmental group and nobody had environmental?
Sir, are you choosing what we
Do the
do?
Marshall thing and wait a year.
My favorite time.
48 people in steel design.
No, like,
Are they really?
Yes.
you say like, if an environmental group had no one that had environmental.
I would be setting that group up for a very rough time.
So, are you setting us up, planning to make our subject, like, are you splitting us up like? Our subject random?
I'm split. Listen.
Oh.
Listen. I'm. No. Listen. First off, I'm going to take your interest at heart. I'm not going to put anybody in an environmental group if they pick environmental dead last. That's not happening. In fact, I'll go ahead and be frank. The people that are potentially going into environmental are folks that pick that as like one of their top 2 priorities. Like, I'm not going to force somebody to pick environmental last. Guess what? That's not going to happen. The idea behind using a random number generator is I do want to split you up randomly, but at the same time, I try and ensure that I'm not putting together a group that's, totally one-sided. Like, if we have an environmental group, I'm going to make sure that there's enough people in that group that have at least had environmental engineering. Because there's some folks who have already taken it, and there's some folks that are taking it next semester. So I'm not going to set a group up for failure. So is it going to be random? Yes, but I'm going to make sure that I'm not setting you up for failure. That's my point. So random with a little purpose. Any questions? All right. Like I said, this is going to be a water resources light review. It is in no way, shape, or form comprehensive. Again, I hope I don't embarrass myself too much, but I think this is the questions that I've compiled are a good review of fundamental fluid mechanics. It's some pretty basic stuff in fluids. It's pretty representative of what you'll see on the exam. And there's a little bit of hydraulics in there. Not really anything on a hydrology side. I was a little hesitant to do stuff with hydrology anyway, since you don't have to have hydrology here, it's an elective, so. But everybody's gotta have fluids, everybody's gotta have hydraulics, so I think there's enough here that you can get a flavor. Okay, so we're gonna start off with some fluid statics and some basic pressure calculations and whatnot, and then we're going to take that and transition into some fluid dynamics, break out some Bernoulli's equation and, look at Reynolds numbers and all that stuff. Okay, so example number 1 is a pretty basic fluid statics problem. This is about, I think, as simple as it could get if you're starting out from square one. So I have a 35 centimeter diameter solid sphere, okay, so it's a solid ball that has a density of 4,500 kilograms per cubic meter, and it's suspended by a cable as shown. Now, it's sitting in a vat of fluid, and half of it is in like water, if you will, and half of it is in oil. Well, it's not water and oil, they're two fluids that are just on their own. But I have half of the sphere submerged in one fluid and half submerged in another. And what I'm ultimately trying to find is what's the tension on the cable. Okay, so let me sort of start this problem out, and I'll walk you through it, but I think you're going to find this is pretty straightforward. So first off, we know that the diameter is 35 centimeters, or 0.35 meters. By the way, a lot of these fluids problems are in SI, so just be aware of that. Okay, so therefore we know the radius is d over 2, which is 0.175 meters. Now, anybody remember how to compute the volume of a sphere?
Diameter squared of 4.
No, that's the area of a circle.
It's not.
Remember that? 4/3 pi r cubed. If you didn't know that, what would you, and you were on the exam, what would you do? And don't say like pray or guess. Or, well, I can't stop you if you're going to start crying, but. Somebody said it? The manual. Look it up. It's in the reference manual. All right. So 4/3 pi times 0.175 cubic meters. So that is what? Everybody in here should have their Casio FX115 ES Plus or equivalent FE approved calculator. I honestly don't know what that is. Find it between now and exam day is what I would say. Oh, at the exam.
0.0224.
0.0224 cubic meters. Everybody okay with this? So if you know the volume of the sphere, how do you determine the weight of the sphere? Well, you would take the unit weight times the volume, right? So we'll say the unit weight of the sphere times the volume. But what is the unit weight of the sphere? Well, do we know the unit weight of the sphere? I don't know what that is. Do we know the unit weight of the sphere? But we know the density. So because we know the density, we can determine the unit weight by doing what? There you go. So rho for the sphere times gravity times the volume will give us the weight of the sphere. So that's 4,500 kilograms per cubic meter times 9.81 meters per second squared times 0.0224 cubic meters, and plug and chug all of that, and what's that going to give you?
99.10.
Say it again?
991.0.
991.0 what? Newtons. Now, let's see if we understand the physical significance. So we have this ball that's being suspended by a cable. Okay. Now ignore the fluid. Okay. Let's say the fluid didn't exist. If the fluid didn't exist, what would be the tension on the cable? 991. Okay. But what's the fluid doing? The fluid is basically pushing up on the cable a bit because that sphere has to displace the volume of the fluid. Specifically, it has to displace half of the lower fluid and half of the upper fluid. So if we can determine the weight of the fluid that is being displaced by the ball, take the difference, we know the tension in the cable. Okay? Everybody okay with this? All right, so what is the weight of the fluid? Basically the weight of the fluid being displaced. Well, here's what I'm going to do. I'm going to say it's half of the volume times the unit weight of the first fluid plus half of the volume times the unit weight of the second fluid. Is that a fair statement? Which is 1/2 V, and then how do I determine the unit weight of the first fluid? Well, I don't have a unit weight, but I have a density, right? So I can take the unit weight, or the density of the first fluid times gravity plus rho 2 times gravity. Now, I'm lazy, so I like doing as few mathematical operations as possible. So each of these terms has a V/2 times gravity common term. So I'm going to pull that out and say V/2 times gravity, and that's rho 1 plus rho 2. Is everybody okay with that?
You walk me through that, Sped.
Just factoring. It's too early or too late or too something for that. All right, so we have 0.0224 cubic meters over 2. Then we have 9.81 meters per second squared. Then we have our differences in our, not differences, the sum of our densities. So we have 1,500, let me follow accordingly. So 1,200 kilograms per cubic meter plus 1,500 kilograms per cubic meter. And so plug and chug that, and what do you get? Say it again.
308.4.
308.4. Do I have a second on that?
No,
No.
I got 296.65.
That's what I got. 296.
296.65 to 296.7.
No, 296.65.
0.7. Deal with it. No. So therefore, again, without the fluid, the tension on the cable is 991, but the fluid is raising the ball up a little bit because the ball has to displace 296.7 newtons. Therefore, the tension on the cable is the weight of the sphere minus the weight of the fluid, which is what?
$694.35.
694.4?
Yeah.
So the answer is what? C. What do you think? That's not bad, right? Any questions on that? All right. Uh-oh. This is a question with words and no numbers. I wish I didn't yeah, they have those things where, you all can use your phones and vote in, like it's Who Wants to Be a Millionaire, and you can, poll the class. I wish I had that set up.
Chemistry?
The clickers?
They have clickers. for
Clickers?
chemistry.
Yeah,
Cl-
clickers.
No.
They're
You
expensive.
say that with ire. Like,
Yeah.
It costs a ton.
I don't even think they use them no more because we hate them so much.
I've never
No,
had
they
it.
still use them.
There's a website that you can do it.
I know, but I know. All right.
Somebody set it up for it.
Okay, let's just, a floating object is stable when what? So let y'all look at it for a little bit.
You just raise your hands.
Okay, let's do that. Who says A?
We read.
Well, here, read it for a second, then we'll do the poll. Let's go.
Let's Google it.
Hey, come on. All right, who says A? Who says B? Who says C? Who says D? Yeah, I have B. Stability for floating objects is defined as any situation where the center of buoyancy is above the center of gravity.
I just remember that, sir.
Yeah, that's what I was going on.
I was just going off C is what you guess. That hasn't worked that well for me. Yeah, I got a 1 out of 10.
Listen, y'all think that's funny? I got 100 on the material test.
What?
They just going off of that.
What? Everybody's looking at their mobile. If that's wrong, tell Dr. Wade I'm sorry, but
You're probably
Because if the center of gravity is above the buoyancy, then you just think of it top heavy.
So you had it right.
That's right.
as I was saying, that is real. I was like, yeah, I had it right. Then everybody's looking at me like I'm weird. I'm like, wait a minute. It's been a while, but I do remember
No,
this
I
stuff.
heard Colton got 100 on a.
That's why I was confused.
The material is.
That's you.
My goodness. I'm moving on. Okay. Fluid statics, breaking out the specific gravity terminology. So we have a cube, 6 meters by 6 meters by 6 meters, and it's half filled with water, and the remaining space on top is filled with oil. So the oil has a specific gravity that's obviously different than that of water. So our pressure distribution is a little different. So what is the total force on one side of the tank? Okay, so let's see if we can figure that out. Now first off, right off the bat, what is, let's see, let's put this up here. So what is the unit weight, well how about this, what's the density of water? 1,000 kilogram per cubic meter. And the unit weight of water is what? 9810 Newton per cubic meter, right?
What's the temperature in the room?
That's right.
That's it.
That's right.
Yeah.
That's right.
What does she say?
So, therefore, what is the unit weight of the oil? How am I going to determine that?
0.8 times 9810.
There we go. So what is 0.8 times 9810?
7,848.
Hold on. Say it again.
7,848.
Okay, sound good? All right. So here's our wall. And let's look at our pressure distribution, right? So first off, hopefully we recognize the pressure increases as a function of depth, right? The deeper you get, the higher the pressure, okay? So what's going to happen with our pressure distribution is we're starting here at the top, and then we go down 3 meters, and we get a pressure. So this is 0, then we have, some pressure 1 right there. But then, so this distance is 3 meters. But then, Once we get below 3 meters, we drop into our second fluid, and our second fluid is heavier, right? So because our second fluid is heavier, the pressure distribution changes, right? So at the bottom, we have P2, and it goes down something like that. Everybody remember that? So, here, I'll walk you through it. So first off, how do we determine pressure number 1? Well,
And then you get a weight times change Y.
there we go. And it's the unit weight of what?
The,
Oil.
The oil times 3 meters, right? So that is 7848 Newton per cubic meter times 3 meters, which is what?
23,544 pascals.
There we go. Now, how do we determine pressure number 2? Well,
pressure
we
number one.
we take pressure number 1 and we add to that the gamma for water times 3 meters. Let's bring it back.
Yes.
So we have, here, let me lower this a little. So we have 23,544 pascals plus 9810 Newton per meter cubed times 3 meters, and that equals what?
$52,974.
All right, any questions? Now that's the pressure, but that's not the force, okay? So how do we determine the force? Does everybody remember how to do that? Well, there we go. So, yeah, what we can do is we can say the force equals the area of the pressure diagram times the length of the box, right? Because remember, the box goes in and out of the screen how far? 6 meters, right? It's a 6 meter long box. So what we can do is we can determine the area of this pressure diagram, multiply it by 6 meters, and there you go. And you'll see how the units work out as well. So you can do this however you want. What we can do is we can say, we can split this up into 3 shapes, however you would like. It's pretty straightforward. So shape number 1 is, so how about this? Let's say 1, 2, 3. So shape number 1 is, what do we got? We have P1 times 3 meters over 2. Is that a fair statement? Triangle, base times height over 2, plus shape number 2, P1 times 3 meters, plus shape number 3 is P2 minus P1 times 3 meters over 2. And then that whole thing needs to be multiplied by 6 meters. So what I can do is, since I'm lazy, I can pull 3 meters out of that whole thing, and I have, what do we have, 23,544 pascals over 2 plus 23,544 pascals plus 52,974 minus 23,544 over 2. And then if I pull the 3 meters out, that's basically saying 18 square meters. So when it's all said and done, what does that come out to be? what's the units? We have pascals times meters squared, so it comes out in newtons. Anybody have an answer? It's big, I'll go ahead and tell you. Anybody?
I'm working on it. I got 900,558.
Do I have a second on that?
Yeah.
And so that's gonna be 900.6 kilonewtons. What do you think? Am I doing all right on the fluid stuff?
Never seen it done like this, but
Seems better than me.
Oh, goodness.
I mean,
You really should just have Martha
No.
why'd that turn into 18?
Well, because, okay,
503.
I pulled the 3 out, here, here, and here, so I had the 6, so 3 times 6, 18. Any other questions? In fair, keep in mind, these are really basic problems, like I don't have any like parabolic surfaces or anything like that, so.
Is that kind of typical for the FE, or is it gonna be all kinds of crazy shit?
Probably not. Now, that's not to say you aren't gonna deal with like circular cross sections. You know, you might have like an open channel flow, like a circular cross section that's only half full. In fact, we have a problem like that. That's pretty reasonable, so, because you can do that by hand pretty quick, so. And I'm pretty sure that the manual, and I might be wrong, but I'm pretty sure the manual has some guides for, dependent upon your cross section, what's your hydraulic radius as a function of how deep is it. I'm pretty sure that there are guides like that in the manual. The one, I have one like this, like that, but it's easy, so you can do it yourself. Sound good? All right, next one. All right, so we have fluid flowing at 5 meters per second into a 5 centimeter diameter pipe section. The pipe is connected to a 10 centimeter diameter section. So what velocity does fluid flow in that section? Okay. All right, so anybody remember what we need to do, or like what type of problem is this? That's a continuity problem, right? AVN equals AV out, exactly right. So the flow in equals the flow out, so
That's what we just did.
what?
He just can't remember what we did last week.
Oh,
Or yesterday.
bless you. So Q in equals Q out, so that's AV in equals AV out. All right? So what we'll do is we'll say that this is obviously flow in, and so the remaining data is related to flow out. So we have a circular cross-section, right? Circular cross-section, so the area in is pi over 4, 5 centimeters squared times the velocity in, which is 5 meters per second. Now, you'll notice I'm being pretty fast and loose with the units, but you'll see what's going to happen here in a second. All right? The area out is pi over 4, 10 centimeters squared times whatever the velocity out is. We don't know what that is yet.
1.25.
Well, you stole my thunder.
Most of us.
The pi's over 4, they cancel. So I have 25 centimeters squared times 5 meters per second equals 100 centimeters squared times V out, and then just divide. So therefore V out is 25 centimeters squared divided by 100 centimeters squared, which is what, bless you, which is why I was pretty fast and loose with the units, because the square centimeters cancel, times 5 meters per second. And that comes out to, say again? 1.25 meters per second. Basically, the diameter doubles, the velocity is cut by 25%. Because flow in gotta equal flow out. Sound good? Okay. Next one. All right. A liquid with a specific gravity of 0.9 is stored in a pressurized closed tank. Okay. So how we handle that pressure is we're gonna have to take that into account pretty carefully. So the top of the tank is experiencing a pressure of 200 kilopascals. So spoiler alert, we're gonna have to take that and subtract the atmospheric pressure, right? Y'all remember that? Take the absolute pressure, subtract the atmospheric. Okay. The tank is cylindrical with a diameter of 10 meters. We have an absolute pressure of 200 kilopascals. What's the initial velocity of fluid when a 5 centimeter diameter orifice is opened at point A? Okay. So does anybody know basically what equation we're going to need to use for this problem? Well, say it again.
Bernoulli.
It's basically a Bernoulli's equation problem. Okay. So let's break that down. Okay. But before we do, a couple of things. Okay. So we have a fluid with a specific gravity of 0.9. So what's the unit weight of this fluid? Well, it's 0.9 times the gamma of H2O. 0.9 times 9810 Newton per cubic meter. And what is that?
8829.
Say it again.
8829.
All right. Sound good? All right. So we have a point A on this structure, and we have a point B, which I'm going to say the point B is right here, where at the top of the fluid. And let's see if we can define some conditions related to Bernoulli's equation, which Bernoulli's equation is that the pressure head plus the velocity head plus the elevation head equals the pressure head plus the velocity head plus the elevation head. Man. It's bringing it back. For me, at least. Now, let's look at point A. We have a pressure head, a velocity head, and an elevation head. Is there any term that we could cancel at point A? The pressure at A is 0, right? The pressure is 0. We're trying to determine the velocity. We've opened that to the atmosphere, right? Because we're setting this equal to 0, the pressure at B is not 200 kilopascals. It's 200 kilopascals minus the ambient atmospheric pressure, right? So pressure at B is 200 kilopascals minus 101.3 kilopascals. What's that?
Oh, we're just talking about getting back to which one's
Do y'all remember this?
Yeah.
Okay. So this is 98.7 kilopascals. See, what you could do is you could say this is 200 and this is 101.3, or you could say this is 98.7 and that's 0. You can do either one, but you're basically saying the same thing. Remember that?
Can you also make your elevation of the day 0?
Well, I'm getting to that. I'm getting to that.
Slow down, Connor.
And so I'm gonna convert that to pascals. Okay? What else can we set equal to 0? Well, you were talking about the elevation head. Well, what we could do is we could say that this is 7 and this is 0.5, or we could say this is 0 and this is 6.5. So what I'll do is I'll say that this term is 0, but with the caveat that the elevation head at B is 7 meters minus 0.5 meters, which is 6.5 meters.
Wouldn't your velocity for B be 0 also?
You need to slow down.
Yeah, I just want to catch up to Connor.
What we've got here is a tank with a diameter of 10 meters. This is a really, really big tank. And so you're opening a diameter that's about yay big, okay? So the top of the tank it's going to be going down, but it's going down so slow that we can basically take the velocity at B equal to 0.
It's always weird, really. Or you just start canceling things out.
It's true. So everything, we pretty much have everything that we need to solve for what we want to know. And what do we want to know? The velocity at A. So therefore, what do we have? We have V squared over 2G equals PB over gamma plus ZB. So VA equals 2G times PB over gamma plus ZB, and then the square root of all that.
Couldn't we also avoid all that and just say square root of 2GH? Isn't that right outside of the orifice? That's the velocity. Daggone it. I'm sorry. I apologize.
Just let me
I apologize. You do you.
Sounds like people learning this.
See? I'll pass this section.
Keep in mind, this is from the structural engineer who hasn't done this stuff in a very long time.
Say we don't need this, we'll just pack up and go home now.
No. You're still doing it. So plug and chug, and what do you get?
Yeah, it's what we said.
And yeah, so the short answer, I understand that there are shortcuts with stuff like this, but I almost wanted to go through the Bernoulli's principle so that you can see, oh yeah, that one's 0 because of this, and this one's 0 because of that. I wanted you to go through that process. So plug and chug, and what do you get for this?
18.62
18.6 what?
meters per second.
There we go.
How many times do we miss up your surprise and let you take section?
Yeah, plenty of chances then.
Yes, sir.
Since it's not mentioned, are we assuming there's no friction loss about the orifice?
That's a great question, and yes, I mean, because you need data. You don't have, now, we've got a problem later where you need to account for friction on an open channel, but you'll see where I'm getting at there. So, but you're also given a roughness coefficient and all that. Sound good? All right. What is the hydraulic radius of the trapezoidal irrigation canal shown below? Okay, so how do you determine a hydraulic radius? What do you do? Well, it's a fraction. What goes on top? It's the area goes on top, and the bottom goes off is the wetted perimeter. Exactly right. So the area divided by the wetted perimeter. Okay? So first off, let's take care of the wetted perimeter first. Okay? What is this dimension? 5 meters. What is this dimension here? There we go. Because that's a 3, 4, 5, and this dimension is 5 meters. So the wetted perimeter is 15 meters. As for the area, we need the area of these triangles, which the area of the triangle on the left and the area of the triangle on the right is just 3 times 4, right? Just add them up as one big rectangle. So, or 3 times 4. So the area is 3 meters times 4 meters plus 5 meters times 4 meters, which is what? 12 and 20 makes 32. So therefore, our hydraulic radius is area over the wetted perimeter. So it's 32 square meters over 15 meters, which is like 2.13. Oh shit, was that a fluids thing or a hydraulics thing? I can't remember. Hydraulics, it's blurry for me.
It's black. Is there not charts in the handbook for that?
I think there are, and that,
I was looking, I can't find it.
well, if I remember correctly, they replaced it with a graph. So like if you have a circular cross-section, you take your depth and then you can determine your hydraulic radius. But I just want to make sure that y'all remember it conceptually. This is something, I'll be honest, I can't quite remember. Let's check. Let's check. Hold on, let's just see. Yeah, when I took my PE exam, I used a reference that that had all of this. And I don't quite remember. It might actually not be in here.
I don't think it is, because I had a question similar to the one you just did, and I had to manually work it out.
Okay. I know the PE exam reference, they have like tables and tables for if you have a trapezoidal shape or if you have a circular shape. And I would imagine if you all took hydraulics, that there's like a table or series of guides in your textbook.
Yeah, Wade always gave us like, all the equations.
Well, okay, I mean, but let me be clear, you're not gonna be given something ridiculous. I mean, there's time constraints as well. All right. Any other questions? All right. Uh-oh. No, a conceptual question.
No.
I'll let you all read it, then we're gonna poll the audience. Hi, Regis Philbin here from Who Wants to Be a Millionaire. Courtesy of our friends at AT&T, right? It sure sucks.
We raising our hands.
All right, who thinks it's A? Who thinks it's B? Who thinks it's C? Who thinks it's D? Okay, it's A.
That's what you use, like when you're scaling up the model to keep it.
Yeah. To create, I mean, basically, remember, the Reynolds number is the ratio of the internal force to the viscous force. So if you want the models to be equivalent, that's like one of the few things that has to be the same. Remember, the Reynolds number is a dimensionless quantity that characterizes your flow, right? Super high number and things are getting a little crazy in here because it's a little turbulent, right? So if you want to scale down your model, you at least need to characterize your flow equivalently. So So the Reynolds number has to stay the same. All right. Last problem. Hydraulics land. So we have a 12-inch diameter concrete sanitary sewer, so it's a concrete pipe. So we have a roughness coefficient of N equals 0.013. Now it flows half full, okay? So it's constructed on a grade of 0.5%. So what's the flow velocity in this sewer, okay? So what we're going to need is the following. And I want to refer to the manual. Let's go to fluids. If you go to the fluid mechanics section, it's actually in the fluid mechanics section if I remember correctly. Right here. We need Manning's equation, okay? Because we have a roughness coefficient, we have a slope, hydraulic radius, which we need to figure out whatnot, all that. Okay. All right. So the nice thing about the manual is it threw in our conversion factor for U.S. units. Since this problem is in U.S. units, all the flows in feet per second, roughness coefficient, so on and so forth. So actually, let me do something real quick. I know this is a hydraulics problem. Here, we'll do this over here. Okay, so on this problem, what they're asking for is velocity, not flow. So we don't need to worry about the Q, we only need to worry about the velocity. Like I said, I'm going to do this problem kind of the long way, just to get everybody sort of, apprised. So what we have is we have V equals K, which is 1.486 over N times the hydraulic radius to the 2/3, and then the square root of S, and because it's S to the 1/2. Okay. Now N in this case is 0.013, so 1.486 to the 0.013. We still need to figure out our hydraulic radius, and I'm going to leave that right here. Yes.
When it's completely full, it's just E over 4 for hydraulic radius, right?
Yeah, but this is half full.
Right.
Yeah. And the slope, now the slope, what was it, 0.5%? So this is 0.005. Oh, I forgot my 2/3. And I'm going to mention something about that at the end. Okay, I'm going to mention something about that. Now, as for the hydraulic radius, again, it's the area divided by the wetted perimeter. So we have, we have a pipe that looks something like this, and what is it? It's a 12-inch diameter pipe that flows half full. So this, that's the flow, okay? And the diameter is 12 inches, okay? So what is the area of flow? Well, it's pi d squared over 4, but it's half that. So it's pi d squared over 8. So pi over 8. Now our area needs to be in square feet, okay, right here. All of our areas and wetted perimeters and hydraulic radius needs to be in feet. So this is pi over 8 times 1 foot squared. So what is that?
0.393.
0.0393?
No, 0.3.
0.393. We have a second on that?
Yep.
Okay, and that's square feet. And then the wetted perimeter is that, right? So the wetted perimeter is half the circumference, right? What's that? Pi r, or pi r or pi d over 2. So the wetted perimeter is pi d over 2. So pi over 2 times 1 foot. And so what's that? What's pi over 2? 1.57, something like that.
1.571.
So therefore, our hydraulic radius is the area over the wetted perimeter, which is what? It actually should come out to be a somewhat nice answer because the pi's cancel.
$0.25.
0.25 feet. Sound good? Alright, so therefore, our velocity is 1.486 over 0.013 times 0.25 to the 2/3 times the square root of 0.005, and that's what?
3.21.
Say it again. 3.21. And so that is going to be C. Now, one of the things you mentioned is that if it was full, it's D over 4. What is D over 4? Well, what's the diameter? Or a foot, right? So what is D over 4?
0.25.
So the hydraulic radius for if the pipe is half full is the same as if it was all the way full. So, same velocity.
So we can just idea before.
But, well, you know that now.
He could have, you couldn't have.
Well, now you can. Now everybody can. Any questions? All right, that actually concludes my my hydraulics and water resources lecture for the day. I'll say this: I was going to include some like rational methods, some Q equals CIA, all that stuff, and a couple other things in hydraulics land, but I didn't.
Okay.
No, in all seriousness, I was getting to the point where I was like, if I can explain this stuff. I don't want to, this is really getting outside my comfort zone, so. Not that no crazy curved surfaces or anything like that. Okay, guys, that's all I have. Next week is our last lecture, and I'll see if I have some more news on teams. We'll see. That's all I got.